All right, you just finished working with implicit differentiation, and you feel confident differentiating with respect to x here. You would just have your 2x dx dx plus 2y dy dx equals 0. Well, what if we differentiated with respect to time t? Because what if we had a rate in which x was changing at a different rate than y, but they were both related by time? Well, I could differentiate this x squared plus y squared equals 4 with respect to t by having 2x dx dt plus 2y dy dt is equal to 0. And then I would have to have other information, but it seems reasonable that I could do this type of mathematics. These are called related rates because the rates are related by time. Let's go to the example that you have on your note sheet. Car A is going west at 50 miles per hour and car B is going north at 60 miles per hour. Both are headed for the intersection of two roads. At what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile from the intersection? Well, we know car A is going left, so we've got that happening, and car B is going up. Okay, that makes sense. So let's see what is happening here. Here's a little bit more of a diagram that models this information. So let's see what we can do. If car A is, let's say, traveling, let's say that this length here is x. Let's say this length's y. They're both varying, right? And let's say then that the distance from, at what rate are the cars approaching each other? Well, wouldn't this be a z? Because that also is something that's changing. Well, is there a way we can come up with an equation to represent this? Maybe the theorem of Pythagoras. X squared plus y squared is equal to z squared. Then we could differentiate with respect to time t. 2x dx dt plus 2y dy dt is equal to 2z dz dt. Now, how are we going to get this dx dt, dy dt? I think I can figure out what x is. It's 0.3. Y is 0.4. And z, well, using the theorem of Pythagoras, would just be 0.5 at that instant. Okay. Now, dx dt, we're trying to find at what rate are the cars approaching each other. Well, that's dz dt, I think. In fact, isn't car A representing dx dt? Isn't dx dt getting smaller? So dx dt would be minus 50 miles per hour. Dy dt, is y getting smaller? Why, yes it is minus 60 miles per hour. And then we have to find dz dt. Alrighty. So, another nice thing with this equation, I could just divide through by 2. Now I'm ready to plug in things. So, I would have 0.3 times dx dt, which is minus 50, and this is minus 0.3 miles. Let's keep our units. So I have miles per hour here, plus, and then y is our 0.4 mile times, and then I have minus 60 miles per hour is equal to, and then 0.5, and that's our dz dt. dz dt. Now, I'm getting nervous, so I'm just going to go to my calculator here. I can take 0.3 times negative 50 plus 0.4 times negative 60, and I'm going to divide that by, I'll take that answer and I'll divide it by 0.5. So I take this divided by 0.5 and I get negative 78. Now Remember, this was miles. I should have put that. So my miles here can divide out. And notice I'll still get miles per hour as my units. So this is going to be minus 78 miles per hour is equal to dz dt. All the news is fit to print. The key problem students have with related rates is that they try to plug things in too early. Start out with an equation in which you want to differentiate with respect to time t. Then do your substitutions. Let's take a look at example 2. Example 2, recall that the volume of a cylinder with radius r and height h is v equals pi r square h. And yes, we'll give you many of the formulas for which you'll need, so don't get too worried about that. Sally places a marshmallow in the microwave to make a s'more. Assume that the marshmallow has the shape of a cylinder with radius 1 centimeter and height 3 centimeters. When she turns on the microwave, the marshmallow starts to expand at a rate of 2 centimeters cubed per second. Assume also that as it grows, the height is always 3 times the radius. Find the rate at which the radius is increasing when the radius is 4 centimeters. Okay, well, we know here that dv dt is equal to 2 centimeters cubed per second. Ooh, okay. That's the first thing we know. We also know that the height is 3 times the radius. I bet we'll use that. Now, if we're trying to find the rate at which the radius is increasing when the radius is 4 centimeters, we probably want to just start with this v is equal to pi r squared times h. Now, if we differentiate with respect to time t here, I'm going to have to use the product rule because r is changing and h is changing. But we also know h is equal to 3r. So probably a simpler way to deal with this might be volume is equal to pi r squared times our h, which is 3r. Well, that's the same thing as volume is equal to 3 pi r cubed. Now, I'm going to differentiate with respect to time t. I get dv dt is equal to 3 pi times 3 r squared dr dt. Now they ask us to find dr dt. I know that dv dt is 2 centimeters cubed per second, so I'm going to have this 2 centimeters cubed per second is equal to 9 pi, and then my radius is 4 centimeters. So I would have 4 centimeters times 4 centimeters, which is 16 centimeters square. Units matter. So I have my 3 times 3 is 9 pi, 16 square, and then I'd have my dr dt. So this dr dt is just equal to, now think about this, it's going to be 2, and I'm just going to have centimeters, right? Centimeters divided by 9 times 60. Okay, so I guess I could say this is going to be 9 pi times 8. So that's 72. And that's going to be I'm going to put 170 over 72 pi centimeters per second. And that makes sense that the radius would have units of, the change in the radius to the time would have units of dr dt. So that is the rate at which the radius is increasing when r is equal to 4 centimeters. Hope this is helpful.